Hey, okay, welcome online class. Welcome to our second lab. And today we're going to continue where we did our first one, our introduction, where we did our graphical analysis. We're going to continue with that and, of course, this time actually get some good data. So let me just say again here that we're going to run this lab as partners. And as I said, I'm going to be the partner that is here in the lab. I'm going to be the partner who has to, and you'll see, walk to the back of the lab and run in the little experiment, then bring it up here, then make the measurements, and then that's where you're going to come in and you're going to actually then read the meter stick and then make the graphs and draw the conclusions, okay? Now, but before all that, before I become your lab partner, let me first be your lab teacher. Okay, so give me about 10 minutes here and say, okay, what are we going to do today? What is the point? And the point of the lab is to make some measurements to eventually prove that the acceleration of gravity is, number one, constant as an object falls, and number two, it has a value of 9.8, or at least close to 9.8, because our measurements will be somewhat close to 9.8. We'll always have some experimental error, and you'll see that in just a minute. But as your teacher first, let's come over here and look on the board here. And so I'm going to put two equations on the board. Equation 1, equation 2. We called these the kinematic equations for constant acceleration. The first one said velocity is equal to initial velocity plus acceleration times time. And so this was chapter 2. This is what we lectured on here in day 2. And this one here was valid only if you have constant acceleration. Now, let me ask this. If I made a plot of velocity versus time, this math, I hope, looks like a straight line to you. Let me remind you of a straight line. A straight line is y equals mx plus b. So in our case, if you change the x to a t, that would be the horizontal axis, and you change the y to a v, then this is saying that the slope would be that number, the acceleration, and the intercepts would be that number, the constant. So what we're going to do is collect some data and plot velocity versus time. If it looks like this, a straight line, then that tells us the two things we're trying to prove today. If it's a straight line, that means it's a constant acceleration. Right? Remember, I'll say it again. This equation would only be valid if we had constant acceleration. So if we drop Bob, and that's the object we're going to drop two objects, Bob and a picket fence, and we plot the velocity, and it comes out to be a straight line, that is our proof that it is constant acceleration. Then, if we look at the slope, note that the slope corresponds to the acceleration, so then we will actually find this constant. And that's the fun part of this lab. So again, we will hopefully make some measurements of a falling object, and we will be able to say, 1, it's a constant acceleration, and 2, it has a value of 9.8, or at least near 9.8. Now let me give you a second equation. The second equation says the position of an object with constant acceleration would be x naught plus v naught t plus 1/2 at squared. All right, let's talk a little math here before we get started. So if I make a plot, and on the vertical axis I put the position of, in this case, falling Bob, and I put time, then let's look at this equation. And so I have a math question for you. If you think about this on the y-axis and time on the x-axis, what shape do you get? Oh, good. I can hear some of you talking at the screen, said a parabola. That's right. You would get a parabola. This is a quadratic equation. And so it should look something like that. All right, so I will say that when we drop Bob, not only will we measure Bob's velocity, but we will measure Bob's position. And when we make this plot, so this will be our second plot. Actually, this will be our first, this will be our second. More on that in a second. But this right here, if it curve fits to a parabola, remember the introductory lab? Remember how we learned about graphical analysis? Remember how we learned how to curve fit? This is why. We learned to curve fit because if I put in my data for a falling object and it matches a parabola, that means it matches this equation, and that's our proof that we have constant acceleration. So in other words, we've doubly proved that we have constant acceleration. If this is a straight line, that's proof that it's constant acceleration. If this is a parabola, then that's proof that it's constant acceleration. And that's what we're going to do. So we are going to measure Bob's position and Bob's velocity, both of those. And when we do that, we will hopefully get a line for this one, a parabola for that one, and hence doubly prove that a falling object has constant acceleration. So that's our goal. And then watch this. Check this out. If we do a curve fit, and of course remember the equation for a curve fit is ax squared plus bx plus c. Now for us, there'll be time. So let me change it to a t squared plus bt plus c. Notice that if we do our curve fit with graphical analysis, this capital A should match up with 1/2 the acceleration. So I'm going to say here that this graph could also give us the value of the acceleration. Its shape proves that it's a constant acceleration. The value of that A should be related to the small a, the acceleration. In other words, it would look like this. The big A that will be part of the curve fitting would be equal to 1/2 of little a. So when we take our data and we do a curve fit, I'll say it again, if we get this really nice parabola, that proves it's constant, but then if we take the value of this a from our curve fit and then bring this 2, we can get the acceleration. And hopefully that'll be close to 9.8. So each graph will hopefully prove both parts. It'll prove A, we have constant acceleration, and it'll prove also B, that we have a value of 9.8. Or at least near 9.8. That's the idea here. And I'll do you one better, because we're going to do this twice. Because we're going to drop not only Bob, but we're also going to drop another object called a picket fence, And this will give us a chance to kind of see some other computer stuff we have. And remember, I'm going to be your lab partner, so I'll be the one hooking up the hardware, but you'll be the one collecting the data and analyzing the data and, of course, turning in the data. And that's where we're going to go. All right, so let me come back over here. Maybe I'll turn this overhead here off for a second. But now let me switch roles. Now that I explained it and I'm going to say, okay, I'm done being your teacher. Now let me be your lab partner, okay? Let's drop the first object and start collecting some data, and then of course put it into graphical analysis. Let's make these graphs and see if both graphs can prove both things, constant acceleration and a value of 9.8, or at least near 9.8. All right, so with that in mind, I'm going to head to the back of the lab because that's where we drop Bob. We have a special equipment over there. And so I'm going to walk around. You guys can get a chance now to actually see more of the lab and our lab tables and some of our equipment, lots of our drawers, more shelving here. But the equipment we need today is over here in the back of the room. And this is our setup. And this is what we affectionately call Bob. We're going to drop Bob. And I want you to see that Bob's got a metal belt, because when I drop Bob, you're going to see this equipment make an electrical spark every 60th of a second. And then that spark will burn little black dots onto this blue, we call it spark tape. And then of course if I take it off, I can go lay it on the lab bench, and then we together can measure where Bob was every 60th of a second. And that's the part that I'm going to ask you to do. I'm just going to lay the ruler out there and have Ron zoom in on it. I'll make some extra dark marks so you can read it, but you're going to collect the data, and then we'll go over to graphical analysis, and we'll do graphical analysis together a little bit, because there's a couple more things I want to show you about graphical analysis that I didn't get a chance to show you on the first day. We did enough on the first day, and we just need to do one step more. All right, but let's actually run the experiment. As I said, all right, so you and I are partners. I'll be the partner, like I said, that'll do the hands-on things in the lab. And so you stand there, don't come out of the camera, just hang on right there. I'm going to drop Bob. All right, so I'm going to push the first button, which actually then makes the electromagnet turn on up at top. And so that's going to hold Bob in position until I turn off the electromagnet, so I can time when I want to drop Bob. All right, so here's the main event. Pushing this next button will do two things. The first one, it'll turn off the electromagnet so Bob will fall, but it'll also create about 10,000 volts that make a little spark right where Bob's metal belt is, and so that will burn into the spark tape where Bob was at that moment. And like I said, that's how we're going to then collect the data of time and distance, in this case position or falling position as Bob falls. Okay, ready? Here's the main event for today. All right, 1, 2, 3, drop. And so zap, 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 zap. There are little burn marks that I'm guessing at this distance you can't really see them yet. We're going to zoom in here, but I have these burn marks here. So I'll turn off the equipment, and I will then take this magical tape, our spark tape, back over to the lab bench. So I'll walk back in the room here. So I'm going to come around and head over to the front of the room here again. And then lay this out. All right. So you guys can read it a little better. I'm going to put it kind of close to you. And I'll just kind of lean over. And so the spark tape doesn't move around. Again, I'm the lab partner with the one doing all the hands-on stuff here. I'm going to I'll move it back to here a little bit. I think that'll be good. And I didn't do a good job. Sorry, you need a better partner. Let me straighten up my tape a little bit. I'm trying to get it to go between the sink here. That'll be good, right? There, yeah. Okay. And let's just collect enough data so that it falls about a meter. So I'll put the tape, the masking tape, on the spark tape right about here. And so now I'll collect the data. Now, since this is our first one together here, let me go ahead and just make a couple of measurements for you, but only a couple, because I'm going to have you do most of them. But see, when I do that, I'm going to kind of block some of your view, I think. In fact, I'll just use the smaller, clear ruler here. But to kind of get us started, I'm going to say that here's a chart of time and here's a chart of position. So I will say at 0 time, I've got 0 position. And then at 1/60th of a second, I will have, now here I need to come over and look at that first dot, and it looks like it is about 3 millimeters. So doing a measurement in meters would be 0.003. And I'll just do one more, but like I said, I want to set this up so you do the measurements.
Seconds.
Oh, yeah, and let me make sure that I put here in seconds. Okay, so the next dot is about 7 millimeters, 0.007, and that is 2/60th of a second. All right, I'm going to do one more. I know I said I was only going to do 2, but I'm going to do one more here before I kind of leave this up to you. That's at about 1.3 centimeters. So 1.3 centimeters would be 3/60ths of a second. Okay? So I know it might be a little hard to see on the camera. So what I'm going to do is make a much darker line, or make a line through the dot. And then have Ron zoom in And I'll put the meter stick on here. And this will be your role, is to maybe even have to pause the video so that you can read the meter stick. And so just write these down, because I want to, well, maybe I'll just show you with graphical analysis here before I put the meter stick on here, so maybe you can read them and type them into graphical analysis. But there is some other things about graphical analysis I need to show you in order to complete this. So I won't put the meter stick on there yet. What I will do is let's turn on the overhead again. Okay? And let me come over to the computer. And let me remind you of how to get to graphical analysis. So I can get to graphical analysis. Let's see. Maybe the best way to show you, since I have my browser here, is to remind you that this website, virtualmachineview.sbcc.edu, is set up for you guys so that you can use all of our software that we have at school, so that you can actually then do a lab off campus using our equipment on campus. All right, so I'm going to click on that again. And this is the place where last week or last lab I said, remember, you can either download the client or you can do the HTML. I'll just do it through the HTML. And here's where, on the first lab, instead of clicking just the program, I should have gone to the desktop, because if you remember, I need to then save my work to either email it to me so I can turn it in Canvas, or also start a browser and go to Canvas when I'm in the virtual desktop, because my virtual desktop and my real desktop on my machine are different, and so I can't print this or access Canvas unless they're in the same place. All right, so that's probably the trickiest thing of the virtual desktop, is getting a chance to turn it in. So here I'm going to click on the desktop, and of course you can see that for me it's listed as an employee and as a student. I don't know how it looks for you. You're going to want to click on the student one, but if I do it, it just crashes because I'm not a student. So I'm going to click on the employee one. So mine will look a little different than yours, which is why last time I avoided that, but then I ran into troubles not having a desktop to save things to. All right, so I'm going to click on the employee desktop and let it do its thing. And ta-da, here is my desktop. Okay, now I have graphical analysis, and interesting, I have graphical analysis here twice. But last time we were using this one, so I'm going to continue to use this one, this top one, and I'm going to start my graphical analysis. All right. Now, this is probably a good time to say, like last time, you probably should put this little video over in a side window, maybe a quarter of your screen, and then use the other 3/4 of the screen, or maybe half and half, so that you can start doing the graphical analysis with me. All right, so as we did last time, Let me use the laser pointer here. Let's change this first column to time, because we want to plot Bob's position versus time. So, working together here, double click this and change it to position. I might as well, oh, I'm sorry, the first one was time, my bad. Yeah, time. So let's do time on this first one. Call it T. Let's measure it in seconds. But here's something new I want to show you. All right, we didn't do this in the first one. We didn't really need it. And I was kind of waiting for this time anyways. But do you see where you can put a little checkbox here that says generate values? You can just have the computer start and end and generate those values. And so you don't have to type in 1/60th, 2/60th, 3/60th, 4/60th. So if you're working with me, follow me and put a checkbox there. And then right here at the start, put 0. And the end is kind of tough to say because I'm just going to go 1 meter and stop. But I know that a half a second falls more than a meter. So why don't I just set it at a half a second, and then I might have too much data in that one, but that's okay. At least I don't have too little. So, all right, so I'm going to end at a half a second. So I'm going to put 0.5. Here's the important one, though, the increment. How big is each of my measurements? And that's where the 1/60th of a second comes into play. But here's the other thing I need to show you. For better or worse, graphical analysis is not that sophisticated. So do not type in 1 divided by 60. It won't do it. You got to change it to a decimal. So grabbing my calculator, which I don't see my calculator, but I'll just do it in my head. 1/60th, I'll just do 1/6. 1/6 is 1 or 0.1666666. So with an extra 0 would be 0.01666666. That's what I need to type in. So I'll say it again. Do not type a fraction. Type a decimal. Okay? So I'm going to type in 0.0166666666 and hit enter. Hope I didn't do that too fast. Type it in and hit enter. Now watch this. Notice then that it made the increments increasing all the way down for a total of a half a second. You can't quite see the bottom, so maybe I'll scroll down on the data table. But there's the bottom. And it looks like with a little bit of rounding, it didn't get exactly 0.5. Maybe I should have done a few more 0.66666s. But however, do you remember the first time we said about significant figures? This is the same thing as last lab, and it's going to be the same thing on every lab. That looks terrible. That is not significant figs. Okay? Now, I know, because I've seen the manual on this, that the clock on there is accurate to 1,000th of a second. Not 10,000, and certainly not a billion of a second, as this indicates. And so that's just wrong looking. Those are math numbers. Those are not science numbers. There is no way that those numbers should be accurate to a billionth of a second. And that's what it's communicating. Like I measured the time to a billionth of a second, and I did not. So, if you remember last time, we went to the options and we could change how many decimal places. Let's do that again. All right, so to remind you of that, I'm going to go to the top of this column. I'm going to double click. Then I'll click on the options tab. Then right here where it says decimal places, I'm going to pick 3 because that's 1,000th of a second and click done, and oh, that looks so much better. See, that is communicating right here a half a second and accurate to 3 decimal places. And of course back at the top, and I'll have to scroll on my data table back to the top. But now I've entered in my time. Okay. Now, the other half of this is the position of it. Okay. So, like we did last week, let's do this. Let's take, double click, and go to where it says name. And might as well put position. And so Bob is falling. For short name, maybe I'll just leave it as a Y. I was tempted to call it an X because that's what I've been doing over here, but it actually did fall down vertically. So Y might be a more appropriate symbol. So I'll leave it as a Y. Under units, I'm going to be measuring it in meters, so again, like we did in the last lab, let me put an M and click Done. Now, let me just point out again, notice it did just like last time. It gave me the name, it put the units in parentheses, it put it on the vertical axis. All those things we've already seen. There are a few more things coming up that you haven't seen, but this is the position. But here's where I'm going to ask something of you independent of me. Is now it's time to enter the position of all those dots. Okay? Now, let me come back to at least the first 4 that I already got started on. 0.03. Well, actually, no, I'm going to let you look at them. So forget I did this. Never mind. Forget I did this. But I will say this. The very first one, you need to put a 0. And so the very, very first one is going to be a 0 because I'm going to put the meter stick right at that first one. And then, and I might have to circle around to the front of my table just to make sure that you're going to be able to read that on the video. And so I've got 0 lined up. I think that is close. And within a millimeter or so, it's close. And I just realized as I look close, because of our meter stick has that metal piece on here, you are going to need my help for the first ones that you can't quite read. So I'll read them to you. The first one is 0. The next one is 0.003 meters. The next one is 0.007. The next one is 0.013, and now I think you can begin to see them better. See, that's a 0.023, that's a 0.35 or 6. And so, Ron, go ahead and just slowly scan across. And I guess it doesn't have to be too slowly because you students, you can hit pause at any time. And you can then read in those numbers. And I'm going to say then, I'm going to start typing in some, I'll call fake numbers.
The pop is really big.
So it looks like our tripod doesn't have a smooth flow. But also, Ron, I think if you just zoom in and then zoom in, they could hit pause on any section of it and find
Make sure not to skip dots.
the data. Yeah, and make sure you don't skip any. Yeah, that is really bad, huh? So we'll try another tripod.
I think I'm going to get off and do it by hand.
You think it'd be better to take it off and do it by hand?
Nah, that's right, 'cause it wouldn't,
Okay.
you back up, so here's this.
But while you continue to help the students see the data, let me type in some fake data. So I'll be working with some fake data, but I want you students to work with the real data. But remember, there's still some more stuff I want to show you, okay? So it looks like you've got all that, Ron. Let me go back and maybe type in just a few pieces of fake data. And I'll stop. I'm sure you guys did not get 49 meters for any of yours. All of yours are under a meter. Okay? So this is where I'm going to let you do a little bit of the lab. So I'll say it again. Hopefully our video came out without too choppy, that you're able to get some data in here. And it probably goes down to about here somewhere, wherever the last one is, it would have a distance just under 1 meter.
I'm gonna take pictures.
And take some pictures. Okay, we might take some pictures and send it to you. That might be better also, or helpful also. But now, I'm going to get a chance to show you what I want you to do on the graph. Okay? Starting with, remember last week? I'm going to say it again. Do you remember that auto scale button right there? I'm going to click on it. And so I'm going to click on this auto scale. And then sure enough, it has put my data here. Okay. Oh, remember last week we did a title, so let's not forget a title. Title's important. I'll double click up at top. Maybe I'll say position of falling Bob. And so this is a falling object. Clearly it's a position versus time, so maybe I won't mess with that, but here is a good title. But here's the most important thing, okay? And in fact, Ron, come back over here where I was being teacher. This graph now should fit a parabola, and from the coefficient in front of the quadratic term, by doubling it, I should get the acceleration due to gravity. And so that is our first of 4 graphs that are going to prove that we have constant acceleration and that value is 9.8. Okay? So you guys have real data. Mine is artificially made, but I did make it so that it would fit a parabola well. And so let's do this curve fit now together. All right, so I'm going to go to Analyze. I'm going to go down to Curve Fits. I'm going to select Quadratic. I'm going to go Try Fits. It does match a parabola really well. And I'm going to go OK. If yours does not match a parabola really well, you've done something wrong. Go back and remeasure your data, okay? Because it will. Now, that being said, this right here proves, as I said, 2 things. Let's take a close look at it. Does it match a parabola? Yes. So it's constant acceleration. 2, does it come out to be about 9.8? Well, let's look. So here's that A I was talking about. It's 3,600. If I double that, I would say the acceleration is 7,200 meters per second squared. Now, with that said, remember mine is going to be wrong because I made up data. But I'm hoping for your capital A you're looking at a number of like 4.8. Because if you double that, you get 9.6. Or 9.7. Or 9.8. Or 9.9. We don't usually get things higher. We usually get them a little lower because when Bob falls, there's a little rubbing on that wire and that reduces the acceleration from just pure free fall. So I don't expect you to get exactly 9.8, but if we did this time, or if you did this time, awesome. Mostly we get about 9.7, and a lot of times we get 9.6. Sometimes we even get 9.5. Now, if you're studying at less than 9.5, I think something's wrong with your data. Okay, so go back and look closely at it. All right. Now, of course, I haven't actually done the data for this one, and I will after the video just to make sure there's not something wrong with my data. But I'm pretty sure, looking at the size of those and my experience, that you're going to get some good data here. You're looking at probably getting a 9.7 or a 9.6. All right. Well, let's keep going, because here's something new I need to show you. Let's do the second graph. I should have said. So before we leave this graph, make sure you save it as a PDF. And that's where I didn't do a good job last time showing you. Hopefully I can do better here. And I couldn't show you because I didn't log into the desktop. That's purposely why this time I did. Okay. Also, on the PDF, I learned that one of the other problems we were having is the Adobe, we didn't have the license for it, at least in this lab. So I don't know how yours is working. So I had to go with the Microsoft PDF. Okay. So watch this. This right here would be the first of your 4 graphs to turn in. And I'm going to go print graph. And I'll put my name on it. But like I said last week, that's not so important for you online people, because you're going to turn in Canvas. I'm going to know who it is. Okay? But right here, when it says select the name of the printer, go down to where it says Microsoft Print to PDF. Because we do have the license for Microsoft, and this will make a PDF for us. Okay? I think last time I was showing you the Adobe one, but every time I tried it, it crashed for 2 reasons. 1, we don't have a license for that, and 2, I hadn't activated the desktop. So it was kind of left in limbo, spinning around here. All right, so I'm going to click OK and watch what hopefully happens. Good. I get a dialog box that says, where do you want to save it? The default's on your desktop, so that's good. It's going to go right to my desktop. I can give it a file name. I won't do anything fancy. How about A for acceleration? Okay. So there's my file name. And then when I hit save, it kind of does its thing. And so when I go back to the desktop, it should be there. Okay? Now I don't want to go there yet because I want to stay here on graphical analysis. But now I want to show you the second graph, which hopefully will prove the same thing. Constant acceleration at a value of 9.8. Okay? All right, so coming over here, here is a new feature. Let me just make the graph a little bit smaller so I can make the data table a little bit bigger first, because I need another column. I need a column for velocity. And that's what I'm going to plot on this vertical axis. And so this is the new thing to show you today. How do I get a new column? It's pretty simple. Where it says data, you can then select data and a new column. Watch. So I'm going to come over here, data, new calculated column. Okay? And so I have a little dialog box that by default says calculated column, terrible name. I want that to be called velocity, because I want to calculate velocity. So I'm going to go V-E-L-O-C-I-T-Y, velocity. And of course, short name, I'll just put a V. Units, since I'm measuring distance in meters and time in seconds, will be meters per second. But the big thing here is what's the equation? Okay, how do I use the data I have to get the velocity? Now, I'm hoping you remember from the lecture today, day 2, the velocity is the derivative of position. And that right there button that says functions will allow me to pick a function, a mathematical function called the derivative. So I'm going to click first on function, and then I'm going to go up to calculus, and I'll pause. So all the mathematical calculus functions are in here. There's a lot of interesting things, but I'm just going to go derivative. Okay, just do the first one. And so I'm going to do derivative. And watch what happens now. I've got the function in the box that says derivative, and then it's got some parentheses saying derivative of what? Well, it's derivative of position. Now, it's position with respect to time, but graphical analysis, the default is respect to time. So I won't even show you how to do it with respect to something else. We'll just always do it with respect to time, and that will always be the first column, and so we'll just say, hey, take the derivative. Okay, so it's the derivative of position with respect to time. So I need to pick the variable position right here. So the second box is the position. And so now it's ready to go. All I got to do is hit done. It's got the derivative of position. That is going to do a calculation to give me velocity. So I'm going to click done. Ta-da! And did you see it? There it is. It gave me a calculation for the velocity. Okay? Now, there is one thing that I want to do, and I need you to do it on yours, but we're doing so many other things. Let me not completely explain why, but in the settings, you can ask the computer basically how many points close in do you want it to use to calculate the derivative. The default is 7. And so what it does is it takes the point you want to get the derivative, and it goes 1 point out and back and gets the slope between those two. Then it goes another one, a slope of those two, and another one gets the slope of those and averages them. And so it's not taking a derivative like you would with pencil and paper like a function. It only has data points. So it actually makes 3 lines out of those 7 points and averages them. That's good that it averages them. It's bad that it goes back 7, or back 3 and forward 3, because what about the first 3 points? They don't have 3 points to go back to. So for something like this, where you only have a few data points, it makes more sense to tell the computer only go back 1 and forward 1 and use those 3 points to calculate it. So, without taking more time to explain the details of the derivative calculation, let's change the settings from 7 calculations to 3 calculations. Watch this. Go to File, go to Settings, and select it. And let me point out then, this is very similar to many times on your calculator where you would select either degrees or radians. Notice default is in radians. So later on in this semester, I will ask you to do some trig calculations, And I will say, wait, you got to go back to settings and change your computer into degrees, because we measured in degrees and the default is in radians, okay? So keep that in the back of your mind. But this is the one I'm talking about. The number of points used to calculate a derivative by default is 7. That won't work well for us today. So without too much of an explanation, let me just tell you, change it to 3 and click OK. And watch these numbers change slightly. So I will go to OK, and they will change slightly. All right. Remember I said now we're set at 3, and that's as small as you can get. Remember I said that the computer is then calling it 3 because it takes the point you want to know the derivative and it goes 1 forward and 1 back. Here's the problem though. The very first point doesn't have one to go back to. And the last one doesn't have one to go back to. Forward to. That really means that this point right here is probably calculated wrong. And the first one is probably calculated wrong. But the others are probably good. So let's see what we got, okay? Now remember, mine is fake data, so you should have something that hopefully looks much better than mine. But I'm going to change the vertical axis to velocity. So I'm going to click right on that. And when I click once, watch what happens. Click. It says, well, of all these columns, these 3 columns, time, position, and velocity, or all of them, what do you want to plot? Well, like I said, I'm already done plotting position, so now let's go to this and plot velocity. That's our second graph for today. All right, so I'm going to come over here and click on velocity. And notice this nice straight line. Except, notice, the first and the last are not fitting right. Those are the 2 we don't trust. And so, let me say it again, as I said at the beginning, if we can make some data, collect some data, and show that velocity versus time in a straight line, we're proving that it has constant acceleration. So I would say we just proved it. We just proved we have constant acceleration. And I would say we proved it for the second time. We already proved it when we did the first graph. Now on this graph, we're proving it yet again. If you look at the first and the last point, you might say it's not a straight line, and that's why I want to keep emphasizing those do not trust. They're messed up. In fact, you'll see something I think a little bit better in the next program I show you. The writers of those programs don't even give you the option to see it. They just delete it off and they don't even show it in their calculations because those programmers, I guess, decided it's not trustworthy. We shouldn't even show it in the data table. So I don't know which is better, to show it and make you understand that it's not valid, or to already say it's not valid and we're not going to show it to you if you try to take a derivative. But nonetheless, slightly different philosophies between those 2 programs. But I'll say it again, and we're almost done, except we've got to curve fit it and change the title. Don't forget that. So remember, we had position of falling bob. Let me go ahead and click on it and now say this is not the position of falling bob, but this is now the velocity of falling bob. And so I'll click on done. And to curve fit it, and even though you've done some curve fit, there is one more thing I want you to see here. I want to curve fit it, but not all the data. See, remember the first one and the last one I don't trust? So everything I've shown you so far, when we've done a curve fit, it's been curve fitting all the data. if you only want to curve fit some of the data, you need to select that data before you go over to the curve fit. All right, so before I go over to the curve fit, I'm going to do this. I'm going to select what I want to curve fit. And watch this. You can see that my gray area did not select the first or the last. You can also see that in the data table where it has selected and grayed in what it's going to curve fit, and it's ignoring the first one in and the last one. And so that's really kind of a big and new lesson for graphical analysis. How do you get a third column? How do you calculate a derivative? What parts of the derivative do you trust in a computer calculation? It depends how many points you choose. So if you choose 3 points, you can't trust the first and the last one. And so we'll curve fit that. Okay, so finally we can curve fit it. And that I know you know how to do. So I'm going to come over to here, and I am going to go Analyze, and I am going to go Curve Fits, and I will scroll up to Linear. I will move down here to Try Fits, and I will pause and just ask, does this line represent my data well? And I would say yes. Notice it completely missed the first and the last data point. And if I'm happy with it, I will click OK. And then this is our second graph. But before I talk about printing it to turn it in, let me point out again that what we talked about earlier when I was being your teacher, before I was being your, well, I guess I'm doing both. I'm teaching and your partner. But remember I said that the straight line would prove it's a constant acceleration, and the slope would give you the value of that constant acceleration. So my slope is 7,200, which is the same number as my other graph, but it's fake data. Yours, hopefully, is giving you a number like 9.6. It's giving you the same one, okay, that you got before. So I would say what we've just done today, me being your hands and you being the smart one collecting the data and analyzing the data, have just proved a falling object has a constant acceleration. You proved it twice. And you also proved it has a value of 9.8. Now let me show you one more time about printing it. So I will print it to PDF, and I'll do the same thing. I'll go to File, I'll go to Print Graph, same name, but as I showed you before, and I think it's still there by default, it is Microsoft Print PDF. That'll put it on my desktop, and I'll go OK. I need to call it something. How about BBBBBBBB? I guess it's still acceleration, but I already did all the A's. This is the second one. So BBB, maybe for Bob. So this is the acceleration of Bob. But so is the other one. But anyways, I'll hit save. So again, hopefully that's on my virtual desktop here. Okay, so I think I'm done with Bob. Let me shut down this program and go to my desktop and just hopefully double check that both of those are there so I can turn them in on Canvas. So I'm going to close down graphical analysis. I don't think I need to save any of these. And now I'm back to my virtual desktop, and there they are. There's that first graph, AAAA, and there's the second one, BBB, and they have the little icon for a PDF file. And that is what, like I said, you want to start your browser, say Chrome, and either A, email it to yourself so that you can then start Canvas and turn it in that way. Or maybe it's probably just easier to start your browser and go right to Canvas and then turn those in from the desktop of the virtual computer. Okay? Now, we're going to do this all again with a new program, and I think you'll find this quite interesting. I like this next program and the equipment that goes with it. It's got some really neat hardware. This actually might make you feel a little bummed that you're not in here doing the lab because the hardware is pretty cool. All right, so here we go. Let me clear off this part of the desk.
Stop the bed.
No, now let it go. I'm going to go ahead.
Oh, I was going to photograph all
I hope it came out well. We'll hang on to that in case we need to photograph it. Yeah. But I think it was coming out pretty good. And I'm going to get the other equipment. Now the other equipment I put over here on the side. And so I have my object that I'm going to drop. And if you remember, I said it was a picket fence. Oh, I bumped it again. Ron, did we check the sound? Make sure you're still hearing me?
Sounds good.
Sound good? All right. But I've got this picket fence here, and we're just going to drop it. And I'm going to put this little foam pad down where I drop it. And I'm going to drop it starting up high so you can see some of it, and you'll see the most important part. And then it'll drop down under the table and then land on something soft so it doesn't break. Now, the equipment that I was bragging about is this cool little apparatus. This is a Photogate, and it really just has an infrared beam across here. And when you hook it into the computer will go, oh, there's something blocking the beam, or oh, there's nothing blocking the beam. So that's all it does. It just says the beam is blocked or the beam's not blocked. But it's pretty clever because as I drop this is why it has clear and black lines in it. So it'll go block, unblock, block, unblock, block, unblock, block, unblock, block, unblock. And so it'll go through a pattern and actually record then the amount of time between block and unblock. And it knows that each of these are 5 centimeters apart. So it's going to quickly transfer distance and time into the computer. We don't have to spend all this time collecting it. That's why this one's going to go so much faster, and it's going to be really neat. And of course, hopefully it's going to give us the same data. Is it a constant acceleration? And is it 9.8? Well, let's see. Now, here's how we have to hook up the rest of the equipment. And again, I'll be your hands here. But you'll see this quite a bit. This box is what we call the interface box. It actually stores the data and sends it over to the computer. So maybe you heard that on the video, but that beep, 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 beep means that I plugged it in, it got power, and it's booted okay. So the two things I have to connect is this piece, which sends the information in to this interface box. The interface box, and why it's called an interface box, is because it translates it into computer information and sends it to the computer. The hub wasn't working this morning, so I'm going to do that. The light's not on. The other hubs were working fine, but mine's not. So I should probably talk to Larry about that. But anyways, that hub I don't think's working. Anyways, so when I was experimenting, I was, yeah. So now we're, I think, good to go here, as long as I start the program that controls this interface box. And so that's called Logger Pro. Now, Logger Pro is made by the same people as Graphical Analysis. So you're going to see this looks a lot the same, and it makes it really easy to use, but it not only makes graph, but it controls hardware. And so that's the extra piece. So let me click on Logger Pro. And give it a chance to connect. Oh, that was faster than I thought. Awesome. Now, for you guys at home, you won't need to completely know this, but I need to then open the correct program that I, as your teacher, have set up that runs the control box and runs the interface. So I'll just launch it for you. The in-person people, I tell them, of course, it's going to be in the physics labs, and it's going to be in either Physics 121 or 105. This one happens to be in 105. This one happens to be the second one in a lab book, and not a surprise, it's titled Picket Fence. So let me just go real quick to kind of launch all that, okay? Now, if everything's worked right, it should be communicating, and it is not. I was concerned a little bit about this, that it may not work through the virtual desktop. I don't know if that's my problem, but you guys at home do not need to launch Logger Pro, because connecting to the hardware you don't do at home. So I'm going to get off my virtual desktop and go back to my real desktop and launch Logger Pro and see if I have better luck here, including opening the correct file. Oh, good. And it says it found PhotoGate and it wants to connect. Okay. So that was a little experiment for me to see if I could really even use the virtual desktop. I didn't think I could, but I thought it'd be easier if I could, so I wouldn't confuse you guys. But I've got to be actually on the network to control the hardware. Okay. There's that firewall thing. All right. Now, that being said, I guess I will turn this towards you, and you'll see a little red light here when I break the beam. See? I put my hand in here. And the picket fence, when it drops down through here, goes on, off, on, off, on, off, on, off, on, off, like that. Okay? So that's telling me it's working well. And so instead of getting little black dots like we did on the first one and then having to lay out the ruler, this is all going to happen in one big swoop. And in fact, look at the data table. The data table is going to have the distance, and I already set up another column for velocity. I figured there was no point in going through a long discussion about taking a derivative again. You got that. So that one's already set up. What I want you to do is to curve fit these plots. So I'm going to collect the data and then give it to you, send it to you. Oh, so yes, you are going to have to start Logger Pro. My bad. You are going to have to start Logger Pro to launch this program. Yeah. But you don't have to control the hardware. So you're fine. But I'm going to send this data to you. Okay? So here we go. Let's actually run the experiment. And you begin by hitting the collect button. So I'm going to hit collect. That tells it it's waiting for someone or something to break this beam. In fact, watch what happens if I did it with my fingers. It would go bloop, 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 bloop. And it would plot all of this. Each time I break the beam with my fingers, it thinks it's 5 centimeters, like the picket fence. And then notice it calculated the velocity by taking the derivative. Notice it also ignored the last point and the first point. So it looks like the velocity of my fingers went down and then up and then really fast. So I don't know what I was doing with my fingers, but the velocity kept changing apparently. Okay. Now, let's do it right. Okay, so let me hit collect again. All right, so I'm going to hit collect. Okay. I'm going to come over here and Just drop it through. And then, sure enough, I have distance and velocity, and here's the two graphs. And this is what I'm going to send to you. And so your job, just like for Falling Bob, is to say, is it a constant acceleration? To prove that, is this a line and is this a parabola? If that's a parabola, it proves it's constant. If this is a line, that proves it's constant, just like we did before. Also, we're going to look at the slope of this one. If the slope of this is 9.8 or 9.7, then that would be the acceleration. We're also going to look at this parabola. We're going to look at the curve fit and look at that capital A. We're going to multiply it by 2, and we're going to see what the acceleration is from that one. Okay? So I'll say it again. This is what I'm going to say. But as long as I still have your attention on the video, and this is still early in the semester, I'm not going to leave this one hanging. I'm going to curve fit it and then take it off and then send you the data. So this is what you should get. Watch this. Why don't I do it in reverse order this time? I'm going to click on the velocity graph. So I'm going to click on the velocity graph. I'm going to go over here to curve fits. So I'm going to go to analyze. I'm going to go to curve fits. I'm going to say, does it fit a linear? I'm going to try fit and say, oh, it says no points are selected. That is my bad. Let me try that again. I probably, without thinking about it, clicked somewhere in the graph and it was just 1 point, and the computer thought, you want me to curve fit 1 point? That makes no sense. So if you don't click on anything, it does all of the data. But if you accidentally click on the graph, this is where you run into troubles. So actually, I'm glad you saw that. All right, so now let me select all the data and do a curve fit. All right, so I'm going to go over here to Analyze. I'm going to go here to Curve Fits. I'm going to select Linear. I'm going to go Try Fit and hit OK, because I'm really happy with that. And this is what I was saying. Look at that slope, 9.79. And so the straight line proves that it's constant. The number gives us the value. And so falling picket fence, or falling bob, or in class falling object, has an acceleration of 9.8. Okay? Now, like I said, I'm going to delete this one off. So that will make you have to kind of do that on your own. Let me show you the other graph too, but I will delete it off before I send it to you. Okay, so here, let's see if this one fits a parabola. So just like we did for Bob, go to Analyze, go to Curve Fit, pick Quadratic, try Fits. And you'll see, wow, it matches it really well. There is our fourth proof that a falling object has constant acceleration. And so I will go OK, and like we did before, look for the term in front of the quadratic. So there's the capital A. Double it. So I'm just going to call that 4.9. And so if I double 4.9, I get 9.8. Yay! So our fourth and final graph does show A, its acceleration is constant. B, its value is 9.8. Okay? Now, same thing as before. Print these to a PDF. Okay? To your desktop. Because these are the four graphs. The two I actually did save, and I called them AAAA and BBBBB. And then these two, I won't bother to actually do it, but you need to do the same thing. This is going to be your lab. In fact, just to give you an idea, here is an in-class person. Here's their first graph. Here's their second graph. Here's their third graph. And here's their fourth graph. Okay, so they printed it a hard copy because they were here in class earlier today, and so they just turned in. You guys need to do exactly that same thing, but to Canvas. All right. Well, I hope that was a fun lab for you. I enjoyed it because I think it hits home that, hey, falling objects, no matter their size, picket fences or bobs, have a constant acceleration of 9.8. We just proved it. We just measured it. We talked about it in class. We proved it here in the lab. And we learned a little bit more about graphical analysis. And we learned about another program, LoggerPro. And that's just going to continue. We're going to learn more about graphical analysis and more about LoggerPro. All right. That's it for now. And I will see you for Lab 3 next time. Bye.